Welcome all of you. In the last lecture, we have seen the interpretation of CU test. Now, the last one is consolidated drained CD test. So, we will see the interpretation of CD test in today's lecture. So, it is all about consolidated drain test, CD test. Just like CU test, consolidation at every confinement alters the initial effective stress condition. At least we have to have 3 samples for obtaining more Coulomb failure envelope and shear strength parameters. So, when we do, we will have at least 3 consolidation pressure or 3 confinement sigma 31, sigma 32, sigma 33 in increasing order. So, at every consolidation pressure, the initial state of the soil gets altered, it undergoes more densification and hence the strength will also be different. So, that is what it means. And why it is happening? It is happening because the initial effective stress conditions are getting altered. Now, we need to keep in mind that the soil samples are initially consolidated in the range close to field condition or design requirement. So, when we apply sigma 3 for any specific field application, so we have some clue about the anticipated overburden pressure. So, the confinement in the field will be definitely sigma dash h, which is coefficient of earth pressure multiplied by effective overburden pressure. So, we know the range what is expected in the field. So, in the lab also the confinement or the cell pressure that we choose will be in line with this. This we have to keep in mind when we are doing triaxial testing for very specific projects where it is extremely important that shear strength parameters should be close to reality. Now, consolidation can be isotropic or anisotropic. That is, what is meant by isotropic consolidation? That is what we normally do. Anisotropic means we can also consolidate at some k0 value for maintaining more realistic situation, because isotropic consolidation, as we discussed in the last lecture, is not actually realistic. We choose it for simplicity. Now, if you choose to have anisotropic consolidation, that can also be done, but we need to remember that during anisotropic consolidation, we are bound to induce some amount of shear stress into the sample. But since the consolidation pressure or confining pressure is not that high, that is not going to create too much of problem, and it is more like a densification. So, it is not going to create much issue, but during anisotropic consolidation we are bound to have shear stress develop within the sample. No excess pore pressure is expected throughout the test, and that is how CD test becomes a very slow test. When you load a saturated soil sample, there will be immediately an increase in pore pressure. Now, we have to do the loading in such a manner that during shearing pore pressure does not develop, and this is a very hard task when it comes to low permeable material. It is practically difficult to avoid pore pressure. So, the loading rate will be excessively slow, and that is how it becomes a very slow test. Similar to UU and CU test, where we have discussed about the stress condition in the soil sample, we will see or we will repeat it for CD test as well. Of course, the first stage is saturation stage. It has to be fully saturated, which is ensured by the B parameter greater than 0.95. So, first let us see the consolidation stage without back pressure. We have seen exactly same for CU test, but it is important for completeness that we repeat this here as well. Total stress sigma Vc sigma Hc, and for isotropic consolidation sigma Vc is equal to sigma Hc. Pore pressure equal to 0 because there is no back pressure. So, effective stress will be sigma Vc equal to sigma V dash C, sigma dash Vc, sigma Hc equal to sigma dash Hc. There is no pore pressure. Consolidation stage with back pressure. So, sigma Vc is equal to sigma dash Vc plus u Bp. Similarly, sigma Hc, sigma dash Hc plus u Bp. Here it is same isotropic consolidation. We are raising the pore pressure also by UBP, so that there is no alteration in the effective stress condition. It remains same as sigma dash Vc, sigma dash Hc as we have in the previous stage. Now here when you apply back pressure, the back pressure line is kept open for drainage as well, and the drainage happens against the back pressure, and that is okay. We should not think that since there is back pressure that is going to oppose the drainage coming out of the sample. This is mainly because UBP is not acting like an excess pore pressure. It is, as I told in the previous lecture, back pressure is more like a static pore pressure. So, any pressure over and above will create a hydraulic gradient which helps the flow from sample outwards. So, that is not going to be a problem. So, back pressure is kept open during the shearing stage as well. So, UBP remains in the sample. So, next comes the shearing stage. So, here the deviatoric stress or the axial stress is applied. Delta U is equal to 0, that is not considering back pressure, okay. It is only for the shearing stage or the loading stage. There is no development of pore pressure, because that is the condition which is important for this particular test. Hence, sigma Vc plus delta sigma is equal to delta sigma 1 dash and sigma 3 dash. So, it is the same. So, there is no pore pressure, so everything remains the same. And here we have sigma cell equal to sigma Vc equal to sigma Hc, which is equal to sigma dash sigma 1 dash C, that is only for confinement, okay. C stands for confinement, which is equal to sigma dash 3 C equal to sigma 3 F equal to sigma dash 3 F. Please note here it is equal. Why? Because shearing stage there is no pore pressure. In the CU test, this was not equal to sigma 3f, sigma dash 3f. Why? Because in the final shearing stage, there will be pore pressure development. So, the final effective confinement pressure will not be same as the initial, the pore pressure will be there. And the final deviatoric stress is sigma 1 dash minus sigma 3 dash of at failure. Now, typical stress strain response of CD test. It is more or less same as that of what we have seen for CU test. There is nothing changing, and that is true also because all these stress strain responses are more or less general in nature. There are two classes as we have seen in the previous lectures. If you consider granular materials, it is loose and dense, and when it comes to clay type of soils, we have based on stress history. One is normally consolidated, the other one is over consolidated. Now, loose sand and normally consolidated clays have same class in terms of stress strain response, whereas a dense sand and over consolidated soil falls in the other class, which has a specific stress strain response. Now, this is not going to change. So, that is why it will look same. You have the over consolidated, normally consolidated and lightly over consolidated. Please remember, the peak of lightly over consolidated is not ensured always. It depends upon how much over consolidation it has undergone. Rather, it depends upon OCR, over consolidation ratio. If the over consolidation ratio is close to 1, it may not exhibit peak, but it is still lightly over consolidated. So, this I will not explain much, it is all the same, and it is plotted with respect to epsilon V. One can always plot it with respect to epsilon A as well. Now, here please note here it is delta V. Delta V is the volumetric change. Now, in the CU test the only difference is instead of delta V there it is delta U. Okay. So, for over consolidated sample there is an initial compression followed by dilation, and for NC there is progressive compression. For the same confining pressure OC exhibits strength higher than NC. Let us say these are all conducted at same confining pressure. We can see that OC is exhibiting a higher strength. OC also has a higher modulus. If you see the slope, this is progressively reducing. So, OC has a stiffer material because it is already subjected to that much pressure in the past. So, it has more stiffness. Sigma df occurs at lower strain in OC than NC. So, these are some very minute important points which we have to understand. The peaking of the OC happens at a lower strain. The peak happens because of dilation and the stiffness of OC material is more. So, all these minute points are important and we have to keep in mind. OC dilates and exhibits strain softening. I will not again get into those details. This has been repeated a lot of times, so you might be already knowing this. NC compress and exhibits strain hardening, and the principal stress ratios just similar to what we have done for CU test. It also exhibit the same kind of trend as we have got for deviatoric stress. Now, typical Morse circle for CD test for NC. So, remember it is CD test for NC. Yes, we have seen, and for NC we need to keep in mind that the failure envelope it passes through origin. So, that is very important aspect which we have to keep in mind. Based on failure stress obtained from triaxial test, MC failure envelope passes through origin. There may be deviation from linearity. Now, this appears to be pretty linear. We can also have kind of deviation from the linearity as well. Now, this may happen if the consolidation stress range is large. This aspect also we have discussed in our previous lecture. As the normal stress goes on increasing, there will be a kind of restriction in the moment. When there is restriction in the moment, the friction mobilized will be coming less, and hence the friction angles start reducing. But at the same time, since the particles are coming closer to each other, it can exercise more cementitious effect. This may not be a real cementitious effect, but when the particles comes closer, there is a kind of apparent bonding that gets developed, because of which the cohesive intercept appears or it becomes more. So, that is what will happen at a higher range, or when we are considering a wide range of confining stress. It can also deviate from linearity if the initial state is different. Now, when we are conducting the shear strength test for specific for a material at a particular place, we need to make sure that we have identical samples. Now, what is meant by identical? The initial state of these samples should be same, and when initial state is same, it means that the initial effective stresses are same. Now, if initial effective stresses are same, it is going to have a comparable strength, but then the strength will be different depending upon the amount of confinement that we give later. So, that is how it works. So, the initial condition of the samples should be similar or identical. Now, if there is deviation from that, like we have a different water content or different density, or even there is change in stress history, then that is going to create, or that is going to give us Morse circle of unexpected diameter. That means it is not a proportional increase in the diameter, rather there will be changes. Now, this exhibits non-linearity. So, that is what it means. Now, if marginal C dash is observed, we know that the soil sample is normally consolidated. we conduct the test and we find that there is a marginal C dash that is coming, we can easily ignore it provided we know that the soil sample is NC. We can neglect this marginal C dash and force the failure envelope through origin. So, this C dash or the intercept can be considered 0. So, that is up to our judgment. So, there are cases where you even though we know for NC it passes through origin, it may so happen that it will not pass through origin and a very marginal C dash is observed. So, neglect that. Now, let us come to a typical Morse circle for CD test for OC. Yes, this we have seen in the CU test as well. Tau versus sigma Morse circle and the failure envelope gives phi dash and it also give a kind of C dash, the intercept. Mohr-Coulomb failure envelope does not pass through origin, and how much the intercept is, that will depend upon the OCR, how much the soil sample is over consolidated. If you remember the plot, we have seen this before. So, this is for NC or critical state friction angle, and we have already seen this response and we have drawn like this. So, this comes for OC. Now, these points where it will fall, this will depend upon the OCR of the sample. So, if the OCR is high, the over consolidation ratio is high, that means that it is heavily over consolidated. If it is heavily over consolidated, the dilation angle will be more. What is dilation angle? This is the angle over and above the critical state angle. Now, this is the critical state angle phi dash C. So, if the over consolidation is more, let us say this is the sigma n. Now, corresponding to this, if the over consolidation is more, then what happens? This point shifts upwards. So, this dilation angle increases. So, that is what it means. So, OCR also determines the kind of C that we are going to get. For OC, cohesion may exist and phi dash would decrease as compared to NC. The phi dash is going to decrease because it is the particles are pretty close to each other and hence the mobilization of friction is limited by its movement. But since it is close by, it develops a kind of cementitious characteristics. I will not say it is real cementation, but a bonding is developed, so that results in a higher C dash than NC and lower phi dash. Now, low phi dash for OC does not mean that the strength will be lesser than NC. It will be still more, as you can see here, this is the OC part from here to here. You can see for every point the strength of OC is greater than NC. Higher stiffness, higher strength for OC, but the strength will depend upon the amount of cracks and fissures. When it is over consolidated, it is also likely to have more cracks and fissures depending upon the kind of tensile stress that gets developed within the sample. Now, this will enable to have lesser strength. So, when we say higher strength, it is not necessarily always higher strength. The presence of cracks and fissures also determine what kind of strength it will have. The strength will depend upon OCR and the confinement. Now, another aspect we discussed earlier is the kind of confinement that we give. Now, when the confinement is more, it suppresses the dilation. So, that also becomes very important. So, that is why it depends upon OCR as well as the kind of confinement, and confinement determines the kind of dilation because confinement can suppress dilation. For determining strength parameter, samples of identical OCR is needed and subjected to different sigma dash C. So, sometimes when we explain based on this figure, there will be a sort of confusion on how the OC parameters can be determined. Now, this remains true. And but in this particular figure there are two things that is happening here. For example, this particular point can be as a result of a particular OCR and which corresponds to this particular confining stress or the normal stress. So, if I redraw this, now let us say that there is an OCR corresponding to which and a given confinement based on which I get a point here. Now, for the same confinement I have a different OCR then or a higher OCR, then the point will go up because it exhibits more dilation. So, that is what is going to happen. So, one aspect is OCR. Now, if you want to determine the strength of a given soil sample, it is ideal to have identical OCR. So, 3 samples of same OCR. So, then what is changing is the confinement. Now, for let us say this is a particular OCR. Now, the same OCR at a higher confinement will give another point, So, this is what we draw and we get C dash and phi dash. So, that is what it happens. So, when you read this particular graph and this particular graph, we need to understand clearly how the shear strength parameters are established for an OC sample. For NC, phi dash from CU and CD may be comparable only if the rate of shearing is comparable. This is very important. Now, why are we doing CU and CD? We have already seen that CD is a slow test, and for most of the time for clay kind of soils we adopt CU for obtaining what? The effective stress parameters. Now, this effective stress parameters have to simulate or resemble the long term condition that exists in the field, which is in fact same as CD. Now, a comparison of CU parameter, the parameter which we obtain from CU and the parameter which we obtain from CD, if this need to be comparable, then it is essential that the rate of shearing also has to be comparable. Again, this is not going to get fulfilled all the time. Now, if the rate of shearing is going to be that slow, CU test also will become slow. So, we need to basically understand there will be some deviation from reality. So, that is the whole purpose of telling here. For OC and dense sand, shear strength parameters may be higher in CD due to the actual dilation the sample undergoes. Now, what this means is that in the CD test, there is actual dilation which is happening, not that tendency to dilate, and the particles have to do the work against the loading. The dilation is a phenomena which is against the loading, against the compression. So, more work is done in this particular case, and hence that resembles in a higher strength parameters in the case of CD. Volume change in CD and U in CU, it is also dependent on the sequence and manner in which the stress changes. What it means is that when the shearing happens, the volume change that happens, because CD is always associated with volume change and U is there in CU. These changes is basically dependent upon the kind of the manner or the sequence in which the stress also changes. So, this also determines what kind of response we are going to get. So, that we will understand with the help of some examples. So, first example is loose sand subjected to compression. Now, we can induce this compression in two different ways. The first way is case 1, that is sigma 1 increasing, sigma 3 constant. This is a typical conventional triaxial testing, which you can see it here. So, here the constant sigma 3, whereas sigma 1 goes on increasing. Case 2 is sigma 1 constant and sigma 3 decreasing. As you can see here, sigma 1 is kept constant and sigma 3 is released. So, what is happening if you have a cylinder which is acted upon by sigma 1, sigma 3, where it may be equal in the beginning, that is what this particular point is. The axial stress is kept constant and the sigma 3 is released. So, when it is released, the tendency of the sample is to compress. So, both action case 1 and case 2 results in compression. So, both the cases results in compression. Now, what is the kind of volume change response that we obtain? It is shown here. Sample can accommodate higher volume change before failure in the case of case 1. For this particular case, the failure happens a bit later. The strain at which the failure happens will be delayed as compared to case 2, where release of sigma 3 results in quick failure. So, a higher volume change can be accommodated for case 1 as compared to case 2. Now, please remember, case 2 is more like a release and this is almost similar to an active condition that is existing in the field. So, when there is a release, the soil sample, the soil tend to expand or it goes away from each other. So, it is a kind of same response that we simulate using case 2. So, we can see that how the manner in which or the sequence in which the stress changes in these two cases will result in a different kind of response. Now, we will see another example, example 2. The earlier one was for granular soil sand, and here we will take an example of NC soil for CD and CU under compression. Again, case is same, increasing sigma 1, sigma 3 constant, case 2 is sigma 1 constant, sigma 3 decreasing. So, it is the same type of response. Now, only important aspect that we need to keep in mind is in the case of comparison, both CU and CD, the shearing rate has to be same. Now, what will be the implication of this on the overall test results? So, for case 1, let us draw the case of CU first. So, CU Mohr circle envelope, phi CU1, that is undrained case. Corresponding effective stress circle is CU effective, which is given by this. Now, this is a drained response. This we have already seen while discussing CU. Now, for the same sample, we have conducted CD test. So, CD test is this. You can see that the strength is higher, okay, for the same sigma 3. Now, this will give us the drained envelope and the failure angle, that is phi dash CD 1. So, this is about case 1. Now, case 2 is sigma 1 is constant and sigma 3 decreasing. So, let us see how we can draw that. Is tau versus sigma. So, for case 2, first let us see CU and we get the CO, and this is the undrained failure, and I will not say failure envelope, undrained trend or linear trend, which is given by phi CU2. The corresponding effective stress circle. Now, here you have to understand, in this case it has moved in the leftward direction because there was positive pore water pressure. Now, in this particular case, sigma 3 is getting released and hence pore water pressure tends to reduce and tends to become negative, because it is a release that is happening for the soil sample, and that is the reason why it is shifting rightwards. And here sigma 1 is constant. So, the consolidated drained test envelope also should start from here. So, that is what you can see, that the diameter of the CD is quite less. Now, why that means that the strength corresponding to CD is pretty less than the undrained case for a constant sigma 1 case. Why this is so, we will explain in shortly. So, the drained envelope or the failure envelope phi dash CD2 Mohr Coulomb failure envelope can be plotted like this, that will give us phi dash CD2. So, we have phi CU1 for case 1, phi CU2 for case 2, phi dash CD1 for case 1, phi dash CD2 for case 2. Now, let us discuss this. So, case 1, this is a typical compression test, right. All of us know only this particular test. Now, for the same sigma 3, CU Mohr circle is less than CD Morse circle, this is quite expected. Case 2, now case 2 is similar to active condition, we have already told this. This is case 2. For Cu, as sigma 3 is released, U will decrease, hence strength would increase. So that is why it is shifting towards right. For CD, now what is happening to CD? As sigma 3 is released, what is happening is, because of this release, it has a tendency to draw water inside. There is a kind of negative suction kind of thing developed because of this release. Now this draws water in the case of drained envelope or drain testing. Now when water gets in, we know that the strength is going to be small, or it is going to fall. So that is what is happening, and hence the strength would decrease, and hence a smaller Morse circle corresponding to the same sigma 1. So CD Morse circle is less than Cu Morse circle. Now comparison of case 1 and case 2. The same envelope which we are showing, case 1. So we have case 1 and case 2. So it is the same figure that we have drawn. Now we will try to compare some important aspects of these two figures. The first comparison is phi dash CD2 less than phi dash CD1. That is, phi dash CD2, the drained characteristics, is less than that what we have from the normal compression test that we do in the lab. So this is an kind of release test, whereas this is a compressive test that is happening. Both are compressive tests, but this is the general triaxial testing that we do. Now note that this particular point, what is the implication of this? We already know that case 2 resembles closely the active condition. Now think of an active condition that exists in the field, and we want to know what is the shear strength parameter corresponding to that. A sample is brought to the lab. This particular aspect is not clear to us, and hence we do a normal compression test, the one which is sigma 3 constant and sigma 1 increasing. We end up with phi dash CD1, this particular value or this particular value, but the actual condition in the field is close to active condition, and hence the available strength of that particular soil will be phi dash CD2. So what we are doing is we are supplying a higher value of phi dash CD1 compared to phi dash CD2. So conventional triaxial compression gives phi dash CD1, which is generally conducted and used. Now for an active condition in the field, the available strength will be phi dash CD2. So if the design value considered is phi dash CD1, then a higher strength is considered than what is available in the field. What is available is phi dash CD2. So these are some important aspect which we need to keep in mind. Now is this going to result in some type of failure? May not be, because we always give adequate factor of safety to account for all such uncertainties. So whether failure occur or not is not the question. What is important is we need to perform a triaxial testing which is very close to the field situation. So that is the whole purpose of this particular discussion. Now at the same time, we also need to keep in mind triaxial simple compression triaxial testing. It looks very simple, but it is really complicated. To get a very good result from triaxial testing, there is a lot of pain involved, and only those who continuously work on triaxial testing will be able to produce a good set of results. Otherwise there will be a lot of oversightedness which is possible in this very simple test, because we have lot of controls in the case of triaxial testing, because of which it makes it much complex than what it appears to be. So there are a lot of things like this, and what actually is happening in the field, and for all those conditions we simply perform a triaxial compression, because that is what is conventionally possible. All other kind of tests need some specific and skilled manpower for performing this, and this is where the shear strength parameters that we obtain from the lab, it deviates from the actual results. And for the same reason, geotechnical engineering or the strength based problems, it becomes highly uncertain, and it gives ample justification for considering these on a probabilistic scale to account for these uncertainties. Just to add to why and what is the implication of these kind of oversightedness or uncertainties. Now case 2, let us make a comparison in this particular case. We can see that this particular angle is greater than phi dash CD2. Now there is not much use of this angle. First of all, it gives a higher design value, and when we design a particular structure, we always need to be careful in the sense be using a realistic value. Now always people tend to be on conservative side if one is not confident about a particular situation. So here phi Cu2 is greater than phi dash Cd2. So anticipated undrained strength is higher than the drained strength, and this consideration may not be appropriate. The first reason is Mohr Coulomb failure envelope is relevant to only effective stress, so only this holds. So phi dash Cd2 is relevant and appropriate, and for any undrained condition we have seen and we have repeated ample number of times, it is better that we go ahead with Tresca criteria and the undrained shear strength SU. Now stress history and CD strength. Consider a wide range of consolidation stress. Let us show it in the form of the consolidation curve E versus log sigma dash. This we have already discussed before. Now point E is on the reloading line, which means that from this particular point C, it is unloaded to D and then it is reloaded to C. Now E is on the reloading path, that means this is C to D. So first C to D happens, and then from D it comes back to C, and E is on that unloading curve. Points A, B, C and F, points A, B, C and F are normally consolidated. D, E are over consolidated. It is very relevant and we have seen this in the previous lecture. So now let us translate these results to tau versus sigma. So what we are trying to do is we are trying to understand how stress history impacts the CD strength. We already know this, but again it is important that we understand this particular point. So here first let us mark the pre-consolidation pressure. So this separates NC and OC behavior. So less and more. So more will be NC. For the same confining stress, strength of OC is greater than NC. That means we are considering point D and A. So now D and A, it is the same stress condition. Now but then D has a higher strength than A. So that is one important observation. E have higher strength than D. Now E is a point, the soil has gone to D and then it is coming back to E. So what is happening is it is getting densified from D to E. So E have higher strength than D because it has lower initial W and lower E, because when the sample comes from D to E, its E is reducing. So for E has a sample with lower E, and hence the strength of E will be more. And here the state of OCR is also different for both D and E. Now this becomes the curved failure envelope, which we have already seen previously. See, curved failure envelope for OC, we have already seen this. Portion DEC is called pre-consolidation hub. So this particular curve DEC, so C will come here, reloading from D, that is from D, and going past C, that is from here it is reloaded to C, and then when it is loaded further it moves along F. So now F is a normally consolidated point and it will have higher strength, but the point will be, so we are dealing with B and then C. So from D to C it reaches here because C is the pre-consolidation pressure. On further loading it goes up to F. So now F is the normally consolidated line. but this particular F has already been subjected to this over consolidation in the past. Once the loading goes past C, now once it goes past C, it erases all its previous memory. So, what has been done in CD link, that particular thing is lost now. Now, once it reaches C, it again comes back to a normally consolidated state. So, that is once the loading goes past C, the previous stress history gets erased. So, now it is left for a new pre-consolidation pressure, maybe at F. So, this becomes a new pre-consolidation pressure if it is unloaded from F. Now, what are the relevance of CD test? The way we have discussed for CU test, more or less it remains same. In fact, those conditions that we discussed in CU test is more appropriate for CD test in terms of its long term behavior. So, relevant for long term stability of earthen embankments, excavations and slopes in soft and stiff clays. So, this is an embankment constructed slowly where drained shear strength of clay will prevail. Now, that is very important when there is a saturated clay and the construction is happening very slowly, then the drainage also would happen along with. There will not be much of pore water pressure development, and hence this will simulate closely the CD condition. Or it can be excavation in clays, or it can be an earthen dam with steady seepage. So, the clay core will exhibit a CD behavior. So, the drained shear strength is persisting for clay core. So, CD conditions are critical for heavily over consolidated soil for OCR greater than 4, and these details are clearly given in Halls and Kovacs book. It is a very fundamental book where all these details which I am discussing is clearly written. So, CD conditions are critical. Why? For OC condition it is critical. We are considering a CD test. Drainage is permitted. Now, it is a heavily over consolidated sample. During shearing, what is the tendency? The tendency of OC sample is to dilate. Now, as it tends to dilate, it will suck water into it. When it sucks water into it, water creates strength to reduce. So, it induces lowering of strength. So, a drained condition in OC is going to be more detrimental because of this particular reason, and this happens mostly in CD test, drained test, where water can easily move in or move out. So, undrained condition, dilating OC draw water into it, causing strength reduction. So, that is what I just explained. So, let us now just try to summarize this lecture. CD test is a slow test and useful only for freely draining soil. So, we have to keep in mind that even though we have understood CD test, it is practically not useful for clays. The MC failure envelope passes origin for NC soil. We have repeated this several number of times, and this should be there in your mind. The MC failure envelope exhibit coercive intercept for OC soil, mostly associated with dilation or cementation if any. As the consolidation, over consolidation increases, that means OCR is more, C dash increases and phi dash decreases as compared to NC. The shear strength parameters of OC soils are influenced by both normal stress and OCR. This also you need to understand very carefully, like OCR also induces changes in shear strength parameters, and the kind of confinement that we give controls the dilation and hence the shear strength parameters. For stability analysis, we have to use Mohr Coulomb effective strength parameters determined for the range of effective stress, effective normal stress anticipated in the field. So, when we are planning the test, we have to make sure that the confinement that we give closely simulates the overburden and the lateral stress condition that is existing in the field. Practically, it is not possible to conduct CD test on clays because it is a time intensive analysis or testing. CU test is a practical method for obtaining Mohr Coulomb failure envelope parameters for clays, provided the rate of shearing is not very high. Now, I just summarize this. A lot of these details on shear strength of clays come from the work of Charles C. Ladd, professor in MIT, USA. So, you can see that in 1970s there are quite a number of reports and publications from Ladd, and many of these details that have come into the textbook related to consolidated undrained UU tests, it is basically coming from his contribution. So, I just want to acknowledge this particular aspect also in this lecture. So, that is all related to interpretation of triaxial testing. So, we have concluded this here, and in the next lecture we will summarize and we will see certain aspects which we have not covered in any of these previous lectures, some very minor important points relevant to shear strength and triaxial testing. We'll have it in the next lecture, and with that the module 2 will be completed. That's all for now. Thank you.